All right, let's begin. This is the calculus homework that I said I was going to do, and finally got the chance to do it here. So this is techniques of integration. I think this is where we talked about the product rule. And so let's go on with it here. It's question 65, 69, 73, and 79 off that homework here. And I have the microphone built on as high as possible. So that means you can adjust it to lower, but I have it on full blast for the microphone part over here. All right, let's go with it. 65. 65 is a very abstract problem. So what I did, you guys think about it to yourself here. After I finish this 65, I give you an example. So those of you that really like to take abstract thought, put it into examples, do it this way. Those of you that would like to see an example first and then take it to the abstract thought, then don't do the video right now. Go look at the example, which is next after this, not this video, but this problem. So go and take a look at the example first and then come back to look at the abstract portion of it. But let's go with it here. So this is what it says. Given function, the reciprocal function, 1 over x, and it's restricted to be x is greater than 0. And so we're not looking at the other side here. We're not looking at this part here. We're just looking at the x greater than 0 part. If we take a point and we take a tangent line, which basically in a sense is the tangent line is hitting, the slope is hitting right here, right? The slope of the line is the derivative. So looking at that and looking at this triangle that's formed with the tangent line and the area that's formed inside this triangle back to the origin along the x-axis and y-axis, this is always going to be, no matter what value you choose, it's always going to be 2 units squared. It's always going to have an area of 2 no matter what, which is kind of funky at first. So let's go through the abstract portion of it. Let's see if this makes sense abstractly. Let's look at an example here. So first things first is I'm going to take a derivative. Derivative of 1 over x, which is the reciprocal functions. You're going to take negative derivative of the bottom value over the bottom value squared. So in this case, you got yourself, there's your derivative. So right, this is going to give us our slope at any particular point along the 1 over x line. But specifically what we want to do is we want to now label a specific point, like that point there. And eventually what we want is we want an equation of this line. So we want y equals mx plus b eventually. This is the long part here. How do we get an equation of that line right there? Well, first of all, we need to know the slope. And then eventually we're going to take a look at the area. And let's talk about the area for now. Remember, this is a triangle, right? So area of a right triangle is going to be 1/2 times the base times the height. Or area of any triangle is going to be 1/2 times the base times the height. But in this case, if you think about, let me switch to laser. How about that? So you guys can see it. So notice that this is going to be our height and this is going to be our base. So if we translate this into categories here, it's going to be 1/2 times the x-intercept, which will be our base, the distance away from the origin, and then the y-intercept, which is going to be our height, which is the distance away from the origin this way. So once we have that, all right, let's go with it here. And then also, again, it doesn't matter which point you choose. So any line that we form was always going to have a area of 2 units squared. So what we do is we have to pick an arbitrary point, and we're going to just call it x initial or x naught. I'm just going to call it x naught. That's the normal way we say it in mathematics. I bet you in physics, well, I think in physics you say it a little differently here. So I'm going to take the value of the derivative at x naught, and that's going to give us that value there. So it's negative 1 over x naught squared. Alright, I'm going to also talk a little faster than normally what I do in class, because I figure you can pause the video and then you keep on going, or else you could slow down the video even if you like on YouTube. So let's go with it. Okay, I already agreed this is going to be our slope. This is our slope of our line at that particular point. So now we have to reach back into algebra. And you guys remember reaching back into algebra, this is called the point slope form. Point slope form says I can get an equation of a graph of a straight line as long as I use this form, and I'm going to plug in a slope, and I'm going to plug in one point. We call it x1, y1. And if I do that, I'm great. So let's plug in our points. So this y and this x are variables. M we just figured out right now. And the points that we're going to plug in are these right here. Right there, that's how it works. Let's go with it. So y minus y naught is equal to negative 1 over x naught squared, x minus x naught. And we have to make it into this form right here. And once we make it into this form, that's kind of cool because remember from algebra, what's my b value? My b value is the y-intercept. So once I get into this form, at least I'll know this value here, which translates to this value here, which translates to the height, which translates the y-intercept. All right, let's go with it here. So first things first, I'm going to multiply into here and into there. So y minus y naught is equal to negative, and we've got x on top, y naught squared on the bottom, or x naught squared on the bottom. So negative 1 times x gives you a negative x on top. That's cool, that's this one here. The next one's going to be a negative 1 over x naught squared times a negative x naught. So in this case, tell me if you guys agree here, the negative times the negative will be a positive, and then since this is on top, this guy's on the bottom, we're going to just lose one of these. So we have 1 over x naught. Okay, I'm running out of room here, so let me rewrite this. On the next slide, we'll keep on going. So that's our problem so far. We're still trying to get into this form right here. So let's go with it here. So let me rewrite it really quick the way we had it over there. And all we need to do now is just to add the y naught onto the other side. So see if this makes sense. All we did is we just added this guy and we brought it over here. Okay, so think about this here. This is the y value. We want everything in terms of x and x naught values. So we got to change this up. And this is not the derivative. This is actually the point itself. So we got to go back to the original function and say to ourselves, hey, original function was a 1 over x. Therefore, it's the same thing as y is equal to 1 over x, right? That's the graph of form, right? So that means y naught would have to have been produced by a 1 over x naught. In that case, we can substitute. I like substitution. So the last value now is just a 1 over x naught, and then we're going to add these guys together. Notice same denominator. So if it's the same denominator, all we do is we add the tops together. So 1 plus 1 is 2. And voila, I got myself a 2 over x naught, everything else repeated. And then to put it into like y equals mx plus b form, I'm going to take this x, I'm going to kind of slide it back over here so that I know what is my x. So that's my m value right there. There's my variable x plus b value, or 1 over x. Now there it is, I got into this form. So I just got the equation of my tangent line. There it is, at that single point. Remember, it looks just like this, y equals mx plus b. So slope is there, that's perfect. But I'm more interested in this guy right here. So the b value, the y-intercept becomes that value there. So if I'm looking at my graph, no matter what point I choose, it doesn't matter which point I choose, the x-axis or x-intercept is always going to be 2 divided by my x choice along the line. Right there. It's always going to be that way because we just proved it with the arbitrary point. Okay, next is we got to fill this guy. So how do we find the x-intercept? I think we do it by plugging in a 0 for the y value this time, right? And we figure out what x is. So let's do that. So here's our equation. Figure out the intercept, sorry, not internet. We want to know this. We have to plug a 0 for the y value. So we do that, plug it in, and then we do some work here. We have to multiply by a common denominator. So looking at this here, I'm going to multiply by this guy squared, right? X naught squared on both sides, because that'll get rid of all the fractions for me. All right, the reason I can do this is because remember our restriction for x is that x is greater than 0, therefore x naught will be greater than 0, and that's why we have that. That's why we're able to do it here. So how about this? X naught squared on one side, x naught squared on the other. 0 times anything is still 0. This was the fun one here. If I bring this over here, these guys are going to cancel each other completely. I'm left with a negative 1 times x, or negative x. Multiplying into here, that's kind of fun. So that means one of these will cancel with all of these in the bottom, and I'm left with 2x naught. Let's bring this guy over. Bring the x over to this side, and that gives me, voila, that is going to be my x-intercept. I found it, I found it. Perfect. Okay, so let's see if I can bring this all together. Here's my points. There's my y-intercept. There's my x-intercept. And now I'm thinking now the formula for the area of a triangle, and I'm plugging it in. So that's my base. That's this part right here. There's my height, or this part right here. And as I simplify it, the x naughts are getting rid of it. Multiply the tops gets 4. The 1/2 turns into a 2 on the bottom, and voila. This is so crazy. Okay, so no matter which point I choose, the area of the triangle that is formed by the intercepts is always going to be 2, no matter what. So no matter if it's up here and it gets this humongous line here, no matter if it's a very tiny, very flat, let's say the point is all the way out here, right? So the tangent line goes like this, and it goes on forever, but it'll still be 2 units. That's cool. All right, let's do an example. Let's do an example here. So, and you're going to see it if you watched the arbitrary video. This will be interesting here to see. So what I'm going to do, this is 1 over x, and I'm going to arbitrarily choose 3. I could have chosen 4, 5, doesn't matter. I could have chosen 1/2, it doesn't matter. I just chose 3 as an arbitrary point. All right, if 3 is my x value, that means on the line itself, 1/3 is the y value. That's cool. And there's my line that's formed. So what I have to do is I have to take the derivative of 1 over x, which is negative 1 over x squared. And then I'm going to evaluate the derivative at 3, which will give me my slope. And my slope turns out to be negative 1/9. Cool, got my slope. That's awesome. So slope of tangent line is negative 1/9. All right, and then I'm going to plug it into form because I think I have, yeah, I do have everything I need. So y minus y1, that's the point that I need, equals my slope times x minus x1, or my value that I chose for that point there. All right, I think I'm good hands here. Let's see, I'm going to distribute the negative 1/9 to the x, distribute the negative 1/9 to the negative 3, which makes a positive 1/3. I am going to add 1/3 to both sides so I can solve for y, and I get this as my final product. Again, slow down if you need to, but notice the 2/3, and again it should have very good correlation back to our abstract form. All right, I think I'm all set. So now let's think of that triangle now. All right. So this is I'm going to redraw it just real quickly here, just so I see it just more like a clear page here. There's that. And just from the previous slide, that was the 2/3 there. Now I got to find that little point there. I plug a 0 in for the y value from the equation from my previous slide. I'm going to multiply both sides by 9. And if I multiply both sides by 9, I get a 0 is equal to negative x plus, will that be 6? Is that right? 2/3 times 9, yeah, 18. 18 divided by 3 is 6. Okay, add x to both sides, and how about x equals 6? So now I know this guy's 6, or 6, 0. All right, now what should we do? We should think about this as a triangle here. So let's separate it. Think of this as a triangle. That's 2/3. That's 6. So 1/2 times the height or the base, whatever. In this case, it's going to be the height times the base, and we get ourselves a 2. That is super cool. I like that. That's awesome. Alright, so those of you that watched this example first, now go back and do the abstract form for 65, and I think it'll make sense. Alright, next one, 69. 69, here it is. It's the derivative of three products at the same time. So number 68, and the textbook actually gives you the formula. You're supposed to derive the formula at 68. And at 69 you're supposed to use it here. But the formula is pretty much is you take the derivative of the first times the rest, then you take the derivative of the second times the rest, derivative of the third times the rest. So we have to take derivatives of this guy. This is kind of set pretty cool for A. Pretty easy here. We got three forms. This is kind of like f of x right here. This is g of x, and that's h of x. And then you just go at it. So let's go for it here. So we'll take the derivative of the first one, which is just going to be a 2, right? 2x plus 1 is just a 2. We multiply by the second one times the third. And in the book, just for convenience sake, I did it as 1 over x cubed, but the book keeps it as x to the negative 3. So it doesn't kind of matter, whatever you like. I kind of like it like this. I prefer positive exponents to my whenever I see exponents, but keep it as x to the negative 130 if you like, or x to the negative 3. All right, plus. First one remains the same. Now we take the derivative of the second one. So the 1 turns into a 0. 1 over x, such as the last problem we did, turns into a negative 1 over x squared times the third factor, really. Then time for this one here. So first two remain the same. Take the derivative of the next one, which would be a negative 3x to the negative 4, and then keep it just like that. I think that's the way the book has it written for the most part, and you're done. If you wanted to simplify maybe a little bit more, you can simplify this into negative 3 over x to the 4th. That's about right, but that's about it. B. Now we're called to do this one. So I didn't kind of think what the book wanted to do here. You could do one of two things here. You could multiply this into this one and this one. That'd be the easiest, right? Or you multiply one of them out. So then you have 3 terms again. Or you could think of this as just the, since there's 4 terms, we're just going to do the same exact pattern, except we're going to use 4 terms, and that's what I did here. So this pretty much is a product of 4 terms. Now how do you take the derivative of that one? The same exact pattern occurs. You take the derivative of the first term, you keep all the rest of them exactly the same. Then you take the derivative of the second term, which is 2x, which is this one right here. So my little laser pointer, there's my derivative. So 2x plus 2. You keep all the rest of them the same. Then we're going to take a derivative of this guy when we get there. So x to the negative 5, x squared plus 2x. And then it's going to be a negative 3x. Oh yeah, negative 3. There you go. That's the derivative of that one. The last one remains the same. And plus now the derivative of this last one here. So we have ourselves the same exact stuff again. And then at the end we have ourselves an 18x to the 8th. And that finishes off the derivative. So we've looked at the pattern. We use that pattern to now take the derivative of 4 factors. Okay, now we'll extend it. Now it goes on even beyond that. What happens if we want to take a derivative of this guy? So x to the 7th plus 2x minus 3. And we have to think about the fact that we have a formula, right, that is talking about 3 things being multiplied together. So in this case, what we want to do here is we want to write all 3 of them out. And there's my, if that makes sense, there's my triplet of my factors, right? So what I'm going to do is I'm going to take the derivative of the first times the other 2, right? Derivative of the second one times the other 2, derivative of the third times the other 2, just like we did for A. So if we take derivative of the first one, it would become 7x to the 6th plus 2. And then the other 2 are going to remain exactly the same. So in this case, you're going to, instead of writing both of them out, how about just put a 2? Okay, here's where the fun begins. The next stage is we take the derivative of the second one, but we're going to get the same thing because this stays the same and that one stays the same. So let's take derivative of this guy because it looks a little better. and then these guys are going to stay the same. So notice what we have. We have the same exact form that we did on the first one. And so if we continue with that, we say to ourselves, hey, if I take the derivative of this one, then it's going to be the multiplication of the first two, which means the first two are exactly the same. So what we do here is we say, hey, look, I have three really of the same exact forms. And so you can write it like this. That's fine. That's what we have over here. All right, now if you know what the chain rule looks like, then this is what the chain rule is all about. It's making this process a little bit faster here. So, sorry, there's a little x squared over there, or a squared over there. So you can write it like this, or you can write it like this. And those of you that are familiar with the chain rule, you'll see like, oh, that is so cool. That is actually the chain rule as a product. And so the chain rule just really makes the product rule go faster. That's all it does. All right, and then the abstract one, D. D is, we're going to take 50 of those. So in this case, you're taking derivative. This is kind of an extension from letter B. Now, remember how we did 4 of them? So the question is, what happens if you do 5 of them, and 6 of them, 7, 10, 15, 25, 50? What's going to happen as we take derivatives of each one multiplied by the product of the previous one? And so let's do that here. So in your abstract thinking, let's go for it here. So I'm going to take a derivative of, let's say this is strung across 50 times, right? There's 50 products here. We're going to take the derivative of the first one, and then there will be 49 that have been unchanged, right? There's going to be 49 of these guys that are going to go keep on going and going and going. Everybody agreed there? So if you get that part, you got it. You got the gist of this, what's going to happen here. So the next one is we're going to take the derivative of the second one, but then there will still be 49, because now we were multiplying the first one and the other 48 of them. And so then you can start writing it kind of like a little faster notation. So okay, if I take the third one, take the derivative of the third one, and there'll be 49 left over. And then I do that again. I'm going to take the derivative of the fourth one with 49 left over. And so now the question is, how many times am I going to do this? I have 50 factors, right? So notice on the previous times, right? When for letter B, we had to do it 4 times because there were 4 terms. In this case, there's 50 terms. So if I keep on going with this, and I finally end it, I'm going to have 50 terms. So it's going to be 50, looks like 50 times the 2x times the leftover 49s. All right, multiply together, gets you 100x x squared plus 1 to the 49. Again, if you know chain rule by now, you see it right away. Like, oh, that is so cool. It's the chain rule in a very quick form. Or actually, chain rule is the quick form of this. All right, next, 73, almost done, or at least we're halfway done. So now the question is this: what happens, or how do we prove something is differentiable at a certain specific point called x naught or x initial? All right, so right above 73, if you notice it has a little box, and it actually talks about what makes something differentiable at a certain point. And so it says this. So the qualifications are, if you take the limit of the derivative as the x goes to x naught from the right hand side, and if you take the derivative as x goes to x naught from the left hand side, remember this is not the function itself, this is the derivative here. It says the derivative is going to exist. So both limits of the derivative exist coming from each side. Cool. Next, that the limits have to equal each other as well. So you know something is different. And I'll explain this. I'm going to go in a little bit abstract. I want to explain the meaning of the definition first, and then let me get you to understand what this is here. So this one says that the limits have to be the same. So not only that, but the limits have to be the same. And then the third part is that f has to be continuous at that point. So it's connected. The limits have to exist, and the limits have to equal each other. What in the world does that even mean? Okay, we'll talk about it. Let's go for it here. So let's say x equals 1. Let me just give you some examples here. Let's say x equals 1. So let's say I have a function that's growing, logistics function or an upside down log function or something like that. Right? When you get to x equals 1, what happens right there? It jumps. Let's say it jumps from that to that. The question is, can I get the derivative at that point? And the answer is no. I cannot get a derivative at that point because it's not continuous. There's a break in a graph, so I cannot take derivatives when we have breaks in graphs. All right, first point. Again, this is kind of going into when you can find derivatives and when you can't find derivatives. And so we say in mathematics, in calculus, we say we can only take derivatives of continuous and smooth curves. That's going to be always. You're going to, if you enter a calculus class, that's what the teacher's going to harp on you. Continuous and smooth, continuous and smooth. And so continuous means they're connected. You can't take derivatives of disconnected graphs. Smooth means there's no corners. There's no quick changes to the slope. So let's take a look at that. All right, here's another one. So it is same exact function coming your way like this. It comes up, and then all of a sudden right here, there's just this little quick sharp turn, and it goes this way. Question is, can I take a derivative right at that point? I know I can take derivatives here, right? I can take derivatives of this right here. I can take derivatives of this one anytime, right? But right at that single point, the question is, can I take a derivative? And the answer is no. The reason for it, it is continuous now, right? There's no break in a graph. It goes from here. I can draw this without lifting off my pencil out of my sheet of paper. It's continuous. But the question is it smooth? So let's talk about this here. So let me back up just a little bit here. So let's do this here. So let's talk about the function itself, because I want to get you guys to understand the difference between function and derivative. So limits of the function. So limit as x goes to 1 from the left-hand side of the function. So how high is this guy going? As we kind of come across here, it looks like the limit's 2, right? That's the height that it reaches, and it kind of just stops right there. So notice from the left side, the limit of the function itself is 2. Alright, now next is from the right side. What's the limit here? Limit of the function as it goes to 1 from the right side. What do you guys say? So this guy keeps on going down, 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 and then it kind of goes right here. It's going to be 2 as well. Good? That's cool. Okay, so establish that. Now think a little bit deeper with me here. Now let's talk about limit of the derivative. So now you're thinking about the slope of the line, right? It's slope of individual slopes as it comes up. So let's go with it. So limit as x goes to 1 from the left-hand side of the derivative. So in this case, this is kind of like a positive. I think it's a positive slope, positive slope, positive slope, and then right over here it's a positive slope, and then it almost like it goes to 0, or you can actually even say it goes slightly negative, doesn't it? But for the most part, I wanted you guys to notice it's a 0 slope, right? It goes to 0. There's a little dip right over here, but 0 or maybe just slightly, ever so slightly negative. So 0 or slightly negative, if you want to sort of call me on it. Okay, what's the derivative from the right-hand side? What's the slope here? Now this is a straight line, and remember the slopes are going to be the same, right, for straight lines. So that is a pretty positive slope, isn't it? That's a high positive slope. That's like 2, maybe 2.5. So this is a positive number. So notice the limits from each side of the slope are not the same. And so we say is that we cannot take a derivative because we can't determine the slope of what's happening right at x equals 1. So in this case, they're not the same. Therefore, you can't take a derivative. So let's one more. So let's say it was like this. Let's say it was a graph that was going up, and it kind of tapered off, and it stopped. And then notice this is a curve, right? This is a curve, and then there's another function. This is just a straight line. It's a straight line. So it comes up to here and then turns into a straight line from here on out. These are two different functions. One is like an upside down log function, maybe upside down log function, boom. And then from here on out, it's a straight constant function. There's two different functions here, but the question is, can I take a derivative at x equals 1? So is it continuous? Yes, no break in the graph. What's the limit of the derivative as it approaches 1 from the left-hand side? So if you think about it here, again, this is the slopes, right? The slopes come together, and the slope looks like is 0. What's the limit of the derivative as x approaches 1 from the left? And this is a straight horizontal function, right? It's slope of 0, slope of 0, slope of 0, slope of 0, boom. Slope of 0. Question is, can I take derivative? Yes. F of x is differentiable at x equals 1. I can take a derivative of that function right at that point, even though those are two different functions. All right. So real quick here, let's just do a quick review, and hopefully this kind of just puts things in perspective here. So you cannot take derivatives if there are breaks in the graph. There's no way you can take a derivative at that point right here of a rational function. Doesn't work. It's not continuous. So also this one is continuous. Notice they actually come together. It's not an asymptote here. There's actually a point right here. But those are, we say those are not differentiable because it kind of meets at a corner and then comes back off. So okay, next one, yes or no? What do you guys say? Yes or no for this one? Can I take a derivative at that point right there? No. Right when there's a quick change to my slope, and I can't take derivatives if there's a quick change to the slope. All right, another one. This one, even though they're going the same direction, they're asymptotes, just like the first one we drew, yet still no, they're not continuous. You can't have it. Okay, 73. F of x is continuous. Yes, I believe so. Right? Is it? Yeah. F of x is continuous. So notice right at x equals 1, those two lines actually come together. I drew my 1 a little bit further out, but it's right there. Yes, they are continuous. Now the question is this: is there a sharp corner? Is it coming smooth in, or is there a sharp twist to the graph? So kind of, is it going like this? Is that what's happening there? That's my question. Or is it more like this? So notice in this one it's kind of coming up a little bit here, and this one is kind of tapering off. So it looks like there's a sharp corner for our slope here. As opposed to here, look at this. This looks a little more smooth now. Looks like it's coming up, and it nicely transitions into another function there. So there's my question. Is it this, a sharp corner, or is it smooth out corner? There's kind of maybe a better example right here. There it is. So there it is. Is it a smooth or is it sharp? What's going to happen? How do we prove it? We prove it just by looking at limits here. So let's figure it out. So it's continuous, yes. At x equals 1, the first function, the x squared function turns out to be 1. The square root function turns out to be 1. So you just plug in the value, and if the values equal each other, that means one graph transitioned into the next graph. That's cool. So now let's take a look at derivatives from each side. So from one side, if you take derivative of 2x, you get x squared, you get 2x. That's cool. So all we want to do is we want to look at the limit as 2x approaches from the left side. Ooh, you know about limits, right? We know about limits. Limits says that if I can plug it in, I'm cool. So can I plug in a 1 into the limit of 2x as x goes to negative to 1 from the left side? Yes, I can plug it in. I can plug in a 1 into a limit. There's no barrier there. There's no fraction that I can't plug in. So here it is. So my slope of x squared approaching 1 from the left side is 2. All right, let's take a derivative of the square root of x. Square root of x is going to give us, that's the square root of 1/2, right? So that's the power rule. Power rule says you take the 1/2, put it out in front, and then you subtract 1 from 1/2, which leaves us 1/2 minus 2/2, negative 1/2. And then what we do is I like to write it like this. Ooh, with a negative. Don't forget the negative here. Oh, I'm sorry, no negative, because it's a 1/2. It's positive 1/2. We didn't take it from the bottom. So let's take a look at the limit now. Limit as x goes to 1 from the positive side of this. Now the question is, can I plug in a 1 into here? Yes, I can. There's no problem here. I couldn't plug in a 0. That would not be good, but I can plug in a 1. And if I do that, I give myself a 1/2. So question is this: is there a sharp corner where the slope changes quickly, or is it a smooth transition? And the answer is it's a sharp corner. As you approach from the left, the slope is getting about 2. As you approach from the right, it's a 1/2, and that means there's like a little corner there. So not differentiable. It is not differentiable at x equals 1. Cool. All right. Hopefully that's a good explanation. I went a little bit more in depth into it just to make sure it made sense. 79, last one here. Can you find? Oh yeah, here's the fun stuff here. So, can you find the nth derivatives of x to the n? Crazy stuff. So let's think about this here. So the first derivative would be this right here, if that makes sense. If I were to say, so if this was x to the 5th, right, or x to the 8th, right, then I would take 8 derivatives. If it was x to the 5th, I would take 5 derivatives. So what happens here? Kind of funny the way it looks out. So the first derivative is the multiplier of n in front, n minus 1. If I do the second derivative, what I'm going to do is I'm going to take, again, derivative again, which now will be another multiplier of n minus 1 in front. It will be n minus 2. And if I keep on going to 3, notice what's happening here. It's actually just the power, the exponents, really. What's happening is the exponents just become factors for my product out in front. And I can, if I keep on going n times, what's going to happen to this exponent here? So if I just keep on going n times, I'm going to keep on going, dot, 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 all the way to, if I'm going to do it n times, eventually I'm going to subtract n from n, which will give me a 0 for my exponent. But what's x to the 0 power? It's just a 1. So this is kind of freaky. You ready for this? If you take derivatives, or if you take derivatives of a power function the same amount of times as is the exponent, you're going to end up with is just the product of that exponent and all the integers below that, all the way to 1. Just the strangest thing. If you want to, go for it. Do an example. See if you guys can do an example off of that right here. Just do x to the 4th and just take 4 derivatives of it and see what happens. Alright, 79 again. Now the question is this: what happens if I do this? I have f to the n. F of x is equal to x to the k, where k is less than n. But I still want to take n derivatives. So I want to be able to take let me see if I can just do an example here, just so it's not so abstract. Because this is beginning to be a little bit more abstract. So let's say this. Ooh, let me get off laser. So let's say we have, but what we want is we want 5 derivatives. So if we say, okay, first derivative is going to be 4x cubed. Second derivative is going to be 12x squared. Third derivative is going to be what, 24x to the 1. The fourth derivative is going to be 24, and here's the fun stuff. the fifth derivative is going to be, what's the derivative of 24? It's a constant term. It's 0. So if that's the case, in fact, anything beyond that, right, it's going to be undefined. You can't take, well, let's say this, I haven't mentioned this in class, you can't take a derivative of 0. So you're done. At this point, you're going to be done. So let's look at the proof here. So if I do this, I do the k derivative. This is from the first time that we did, right? It's going to go all the way down to this right here, right? So if I keep on taking derivatives, this is from the previous one, all I'm going to end up with is k values all the way down to a multiplier of 1. If I go any more, if I just go one more at k plus 1, which means I'm going to take one more derivative. If I do that, the derivative is going to be 0, just like we did in our example. So in this case, here's our conclusion. And this little guy just means therefore. Therefore, if f of x is equal to x to the k, and n is greater than 0, so f to the n is going to always equal a 0. It just becomes a 0. You can't take more derivatives than you have powers of. You're done. So you get 0, because it's just about products. Alright, and the next one. Next one is, what's the third derivative of that right here? So as we've been studying, right, you could do it the long way, you could do it the short way. Let me do it the long way, and then you can say, oh, that's what I just learned here. So if you take derivatives, what's going to happen? The 2 is going to go away. The 7x becomes a 7. 3x squared becomes 6x, and this guy becomes 36x squared. Take a second derivative. Now the 7 is going to become a 0. The 6x becomes a 6, and all we're doing is multiplying 36 times 2 makes 72. You take a third derivative, and you end up with 72. So that's exactly what we've been talking about right here, right? If you're going to take derivative of a power function, these eventually become zeros, 0, 0, and then all you got to do is just take derivative of 12x cubed, or multiply 12 times 3 times 2 times 1, and you'll get what you want out of it. So 12 times 3 times 2 times 1. Alright, in the abstract form, what's going to happen here? If you are here and you want to take n derivatives of this guy, so all the ones that are less than n are just going to become zeros. They're 0, 0, 0, zeros. So at the end, you're just going to wind up with the product of the coefficients all the way to 1 of your leading term. That's it. So hopefully the example kind of helped as you went to the abstract form. All right.